Good morning and thanks for attending this presentation. The title of this work is Robust Control for Reusable Rockets via Structured H-infinity Synthesis. I would also like to acknowledge my co-authors for the help in developing this work. For what regards to the contents of this presentation, first I would like to say something about the motivation for this work, which is linked to the Callisto activity. Then we will have a look at the vehicle and the mission that have been used for developing the work. We will see more specifically some features of a structured robust control, which is the focus of the work developed here, presented here. There will be some numerical results coming from its application, and finally there will be some conclusions and an outlook for the future. So, for what regards to the motivation of the work, as I said, it is linked to the Callisto activity. Callisto stands for Cooperative Action Leading to Launcher Innovation in Stage Toss-Back Operations. It is a trilateral cooperation between DLR, CNES, and JAXA. The idea is that the three agencies together will develop a demonstrator aiming at maturing critical GNC technologies focusing on reusability. The demonstrator will fly from Guyana Space Center at the end of 2022, and since the focus will be on reusability, the idea is that up to 10 repeated flights can be performed with the same demonstrator. So let's have a look at the vehicle and the mission. For what regards the vehicle, we are working with the 40 kilonewton class rocket, which is depicted on the right side. The engine is mounted on a gimbal system to provide the thrust vector control capability, and therefore this TVC system will provide pitch and yaw control capability. At the same time, on the right side, you can see that on the top of the rocket we have 4 steerable fins which provide aerodynamic control in the phases where we experience large dynamic pressure and not necessarily the engine is on. In the phases where the dynamic pressure is low, we will rely on a set of 8 reaction control system thrusters which are also mounted on top of the rocket. For what regards the mission that we are working on, this is essentially return to launch site in almost return to launch site scenario. We have the ascent phase that is depicted here in green, together with the boost back maneuver, which is aiming at inverting the direction of the velocity vector. At a certain altitude, then we have the MECO command, which is issued, and we start the aerodynamic descent, where we mainly rely on the aerodynamic forces generated by the vehicle to control its trajectory. At a certain altitude, we reach the critical altitude at which the GNC will command a reignition of the engine, and therefore we will enter into the powered descent and landing sequence of the flight. This phase will be completed once that we have pinpoint landing, and therefore the vehicle successfully lands on the platform. So let's say something about structured robust control. In general, robust control techniques are frequency domain techniques where we have an augmented plant for synthesis depicted here in the classical scheme, which is recovered from the famous book Multivariable Feedback Control from Skogestad and Postlethwaite. The idea is that we have this augmented plant which is only used for synthesis, in which we can include some weighting functions which will provide the frequency domain requirements that we want to be satisfied. This kind of techniques enjoys guaranteed stability margins, and they also allow the inclusion of uncertainties. These benefits are common to the to the classical H-infinity control techniques. At the same time, in the last years, a specific subdomain of robust control techniques were developed, and these are called structured robust control techniques. In this case, we do not let the optimizer determine the size of the transfer function representing the controller, but we will rather define a template for the controller, so a specific structure for the controller, and the tool will only try to determine the values for the free parameters of our control template. This kind of technique represents a very powerful trade-off between the standard classic control, where we have, for instance, a PD controller or a PID controller, and the original full H infinity synthesis domain, where we can have very nice performance, but at the same time the controllers might have a very high degree, very high orders, which might be complicated to implement on a real computer, or might also be sometimes difficult to fully understand, and therefore also to validate with the classical industrial standard for verification and validation. Therefore, structured robust control technique represents an ideal trade-off between the performance and the complexity that we want to have for our system. So the idea is to apply the structured robust control techniques to the aerodynamic descent problem. In this case, we will apply it to both trajectory and attitude, and an overall scheme is depicted here on the right side. We have the guidance module, which will provide reference position and velocity, and these signals will be basically tracked by the outer loop. In this case, since we will rely on the aerodynamic forces, these aerodynamic forces are dominated by the Euler angles and therefore by the attitude of our rocket, and therefore these Euler angle signals will act as control signals for the outer loop. They will therefore be the reference values for the inner control loop, where we will use instead the fin deflections, such that effectively we can generate some torques, and we can as fast as possible generate these torques such that the actual Euler angles will correspond to the reference values that we want to be reached. At the same time, we will feedback the position and velocities, which will be used by the outer loop to generate the error signals to be combined with our control, such that we can generate the proper control signals for the outer loop as well. In both cases, for outer loop and inner loop, we will use a simple control structure. More specifically, we will use LQR for the outer loop and PID for the inner loop. Since our system is nonlinear, we will apply a simple rule to come up with a gain scheduling nonlinear controller, and we will validate the single LTI controllers by using typical linear analysis methods like time domain and frequency domain methods, while we will apply for the nonlinear analysis a simple full-blown Monte Carlo analysis, where we can verify the behavior of the nonlinear controller. So let's say something about the aerodynamic descent problem formulation. The problem has been formulated in target-centered downrange, cross-range, altitude coordinates. On the right side, you can see the 6 DOF nonlinear differential equations representing the motion of our rocket. We have differential equations for position and velocity for what regards the translational motion, and in terms of Euler angles and angular rates for what regards the attitude dynamics. As I said, for the outer loop, we will have as control signals the Euler angles, and therefore this will be used as feedback controls for trajectory tracking, while for the attitude control we will rely on the fin deflections. Since this set of equations is a nonlinear set, we can apply linearization of the equations of motion to come up with the LTI form of our system in different points. For each of these points, we can define a set of corresponding weighting functions W, and therefore we can build an augmented plant P, and we can synthesize both structured and full H infinity controllers. At the end of the process, we can simply apply the gain scheduling rule that we defined and come up with a nonlinear control strategy. So let's have a look at some numerical results. The first step was to, once that we developed the framework, was to apply it to reconstruct a baseline controller, and this was done for both the roll and the pitch controllers. The design, here on the right side you can see the plant and the corresponding augmented plant including the weighting functions. The design, as I said, includes the actuator dynamics as well, and the chosen structure was a PID controller. The tuning was performed by using a mixed sensitivity design, and as you can see here, where we have some weighting functions penalizing the control effort and the error, which is basically embedded in the sensitivity transfer function. The idea, so the question might be, why doing this baseline controller reconstruction? The idea was that since we will also apply the same framework to come up with the full H infinity controller, we wanted to range from the entire possibilities going from the very basic baseline controller up to the full H infinity controller, and have the entire possibility of trade-off between the two extremes. So the baseline controller, which does not perform very well but only makes the system stable, was at the lower end in terms of performance, but the simplest possible control solution that we could have. So on the right side here, you can see the frequency domain overlapping of our structured strategy and the baseline controller. You can see that by carefully choosing the weighting functions, we could reconstruct accurately the original baseline controller, confirming that our framework was able to capture the lower end spectrum of the possible control strategies that we could synthesize by using the framework itself. These results are also confirmed in terms of time domain, of course. So you can see that the two step responses agree quite well. In blue, you can see the structure H infinity control response, while in orange, the baseline controller time domain response. A similar process has been applied to the pitch control. The only difference is that given the nature of the plant that we have for the pitch dynamics, an extra term was added on the input in terms of input disturbances in order to avoid zero pole cancellations. Again, also in this case, we were using mixed sensitivity design, where we were penalizing the transfer function and the control effort. And also in this case, we were relying on a PID controller. In this case as well, we can see that the framework was able to capture the original baseline controller, and this is visible both in the frequency domain, as you can see here, as well as in time domain, where you can see that even if, as I said, the baseline controller was not performing very well, and we were only interested to have the framework able to reconstruct this type of performance if we wanted to. And this is what we see here in for this step response for the pitch dynamics. So once that the baseline reconstruction was completed, we performed the retuning of the controller. As a requirement, we had at least a gain margin equal to 6 dB and a phase margin equal to 30 degrees, and we were keeping the same PID control structure and the same type of synthesis for the controller, but we were just varying the weighting functions. At the same time, you can see that we were not only applying structure H infinity synthesis, but also full H infinity synthesis to measure the performance loss coming from imposing the structure to the controller. You can see that in basically the two controllers agree quite well in terms of behavior in frequency domain, and this resemblance of the performance is also confirmed in time domain by looking at the step response for the roll control. The same process was then applied to the pitch as well, and also in this case we had the same requirements, and we can see that even if not exactly like for the roll control, in this case we have still similar performance for what regards the frequency domain behavior of the full and structured controllers. This is also in this case confirmed by the time domain analysis, where we can see that the two controllers behave in a very similar way also in time domain, of course. Finally, we performed the control synthesis for the outer loop. In this case, since we were working with the full MIMO controller, which shows an LQR controller, and we were performing the same type of mixed sensitivity analysis for the control synthesis, and the frequency domain results are depicted here on the right side. In this case, the similarity between structured control and full control is even larger than for the attitude, and this basically confirms that the defined LQR structure for the controller is a good trade-off because it does not generate a large reduction of performance while still keeping the control structure quite understandable and easy to verify. In terms of time domain, we got a confirmation of what we just saw in frequency domain, where we basically see that the step response in terms of cross range and down range are very similar for both structured and full H infinity synthesis. And in this case, we can also see that we have a nice decoupling between the two different channels. So when we command a step for cross range, we do not experience large coupling in terms of downrange, and vice versa when we command a step for the downrange. So with the confirmation for all the LTI systems in terms of performance, reduce the performance loss when we go from full H infinity to structured H infinity, it was then necessary to validate also the nonlinear control coming from the application of the gain scheduling technique. To do that, we run a full-blown Monte Carlo campaign with 200 cases, and these cases include non-correlated aerodynamic uncertainties, atmospheric dispersions, wind profiles, and as well as MCI and actuator errors for all of the actuators that we have in our system, and we were also including some communication delays coming from some specs of our onboard capabilities. Computer capabilities. What we see is that the attitude errors were within some prescribed error bounds compatible with our requirements. You can see here an overview of the results that we got in terms of Euler angles and in terms of angular rates, and we could draw similar conclusions for position and velocity errors, which are also within the expectation. You can see on the left side here specifically downrange, cross range, and altitude behavior, while the velocity components are depicted on the right side. Notice that there is some increase towards the end, but this is only due to the fact that we are switching from aerodynamic control to the powered descent and landing control strategy, and therefore there is a variation of the error at the moment of switching the control strategy. Finally, all the 6 DOF trajectories are stable, and you can have an overview of all the trajectories that we obtained here on the right side, where you can see that the aerodynamic controller is clearly capable of reducing the final error within the prescribed boundaries before switching to the power descent and landing control strategy. So, to conclude, we could see that the proposed method allows a flexible trade-off between the complexity of the control structure that we define and the upper bound in terms of performance, which we might obtain if we do not provide any constraint in terms of control structure. The method itself is able to deal with both the outer and the inner loops of the aerodynamic descent control problem, and could satisfy both the gain and the phase margin requirements that we had for our system. This was valid for the single LTI controllers that were defined, but the overall nonlinear, the validity of the overall nonlinear control strategy was confirmed by a full-blown Monte Carlo analysis analysis which was showing errors within the prescribed bounds. For what regards the future extensions of this work, we foresee a comparison of performance between the two loops strategy which we proposed here and a fully integrated 6-DoF control strategy where we control both position and attitude with the single unified controller. Moreover, we plan also to improve or at least to test different gain scheduling rules which go beyond the pure heuristics that we were adopting here. Finally, we envision a more systematic inclusion of uncertainties to verify the design with the linear analysis as well, when we know that some specific uncertainties occur on some elements of our LTI system. While in the case here, they were only verified a posteriori with the Monte Carlo analysis. This concludes my presentation. I would like to thank you for your attention, and if there are questions, I would be happy to answer. Thank you.